Let us get started. Hello. I know you're so excited to be in this class, etc. and whatnot. That's why you're talking, but we really need to finish regression this week before you go to spring break, so that I can give you an assignment, but you don't have to return it during spring break. You're going to have to return it after spring break. So, if you're taking some time off, you don't have to worry about it during spring break, but then you'll return it the week after. Okay. So, win-win for everyone. I wanted to point your attention to a new policy that's effective immediately, and I will send an announcement. While I do encourage you to work together for assignments, okay? And I love that. I want you to keep doing that. You are not allowed to share your assignments with others, because there's a risk that your assignment might be used as is, and that's a misrepresentation. So taking someone's work and presenting it as their own. Okay, so, and besides, it's not really helpful when you are trying to help your colleague. Don't show them your code, because once you see code, it's going to be stuck in your head. You're not going to think of any other way of writing your code than the one you saw. Okay, so think of the code as the incarnation of an idea. Okay, the representation of an idea. And in a way, the idea itself is not sort of, you can share an idea, okay? And that's, discuss kind of how you, for example, you want to sort an array, or you want to look for the temperature distribution. You discuss the idea, say, okay, we need to loop over the values of age, and then we need to create a linear space and solve the linear system. Definitely discuss those things. And then, your colleague might ask you, hey, remind me, how do I do the lin space?
Something juicy. Where is this being? My space. Actually,
guys, would you mind muting yourselves on Zoom? This it's an interesting story, but
that's a little rebellious.
Okay, so let me mute.
One time I snuck out and slept.
Okay, I am muting. Okay, it's an interesting story, I know, but we will discuss it later. Okay, so just be careful. You're not really helping anyone by giving them your assignment. Think of your assignment as your own original product incarnation of an idea, and that is yours. Okay, if you give it to someone else, you're not helping them first. That's what worries me the most. Eventually we all learn from each other. I myself learn from code on the internet. I look at it and I try to mimic it. If I need to reuse a piece of code, then there are software libraries available for you to reuse that code, right? But as the end user, at least in this class, you cannot present someone else's code as your own. So you will both be held accountable, be held at fault from here onwards. Okay, so effective immediately. I'll send an announcement reminder to everyone. Okay, if there is striking similarity between two assignments, and we can tell that very quickly. Okay, it's not a threat, it's more like, I know you want to help each other, but help each other in a way that's actually helpful. Don't give the answer to your colleague. Go through it with them. Tell them, okay, maybe you should do this. Here's how I did it. For example, show them a piece of the code. That's fine, right? But you give them the entire code, that's not helping them. Good. Absolutely, yes. Yeah, so it's going to be on a one case basis. So if you're working together, and we can usually tell from the result if the code was flowing from one direction to another versus this was a collaborative effort. But still, you should try to reproduce. I mean, you discuss the thought, okay, here we need to loop over the values of H. You know, do it your own way and let your colleague do it another way. Now, there might be like 2 ways of doing it, right? But change, you know, you might use a different variable name. You might use something different, but it should not be the same, okay? It should not be the same, all right? Usually we'll be able to tell if there's flow from one direction to another. And, you know, that's not really helpful, okay? So I hope this clarifies things, but I don't want to discourage you from working with each other and, you know, discussing things, but please use the resources that are available to you. Like, I sit in my student hours and I'm like just hanging out there and no one shows up. And I try to put those student hours to maximize the number of students available during those student hours. The help sessions, likewise, I'm not seeing many students show up to help sessions, or even direct communication with me and the TAs or on ed discussion. Very rarely I'm seeing those. And so and the anonymous feedback has probably been the kind of the most the most in demand with these kind of muddy points, but that's not helping you with coding. If you need help with coding, you need to come meet with me, meet with the TAs, okay, and come to student hours, come to help sessions, or email at discussion. Okay, I really don't know what else to do to try to kind of break that barrier. Okay, clearly waiting for the last minute to do the assignment, you might be inclined to just copying someone else's work. Then that's definitely a case of misrepresentation, and you know that can get you in trouble. I've never had to report anyone in my life, in my career here at the university, to the department, but in our department they have a policy like 2 strikes and you're out of the program. You know, why risk a silly assignment that's only like 2.5% of your entire grade, you know, risk losing your entire reputation for 2.5 points, okay? So don't do that. All right, we're gonna continue with the regression. Last time, we finished our discussion on errors and the standard error, standard deviation. I hope that was fun. I hope that was useful. There's videos on YouTube from, you know, recorded this year. I haven't uploaded that yet, but the recording from last year is fantastic, as good as this year's. And so, you know, keep those in your reference sheet in the future as you are looking to do regression analysis. But now we're going to come back to improve our regression modeling capability. So far, we regress data to a straight line. Many people call that linear regression. I like to be a little bit more rigorous and call that regression to a straight line, because linear regression, as we will see, means something different, at least to this observer here, okay? At least to me. So I'm going to ask you this question now. Suppose now we had data that looked like it belongs to a parabola, okay? So a quadratic. And you might say, maybe we go ahead and fit a quadratic form, a0 plus a1x plus a2x squared. We're given x and y data, okay, they're scattered, and you need to fit this parabola in the least squares regression sense. Now, the question is, we need to develop the system, you know, you minimize the error, etc., all of that, and come up with a system of equations for a0, a1, and a2. Do you think that system of equations is linear or not? And why not? Just intuitively, okay? Describe why. So you take this model, right, like we did with the straight line, you define the error S and you minimize it with respect to a0, a1, and a2. Do you think we will get a system of linear equations or nonlinear equations? The model itself is nonlinear, right, because it has x squared. But is the resulting system of equations that you need to solve to obtain a0, a1, and a2, is that linear or not, Nathan? Mm-hmm. Mm-hmm. Yeah. Yes. Yes. You are. I agree with you. Does anyone disagree with Nathan? Yeah. So the model is nonlinear, but the coefficients, which we care about, right? So the model, the X values show up non-linearly, but those are given to you, right? You have the observed data, the XI values. Once you plug in a value and under XI squared, it becomes a number. That's it, doesn't matter. What matters are the unknowns. And those unknowns show up linearly, the shown in red, A0, A1, and A2, right? And yes, indeed, if you do the procedure, you will get a linear system of equations. So you can do it together. We define our total error. S is sum of yi minus fi squared. Remember, yi is the observed data that's given to you. Fi is your model. So in this case, that's A0 plus A1 xi plus A2 xi squared, okay? And then you say S is minimum if its derivative with respect to all of the unknowns, A0, A1, and A2 are 0, okay? So you plug that in, you simplify, etc. You see how the A0 and A1 and A2 are showing up linearly, right? They're not under sine or cosine or any complex nonlinear formulas. They just show up linearly, and bam, you write this as a system of linear equations, okay? Now, there's a pattern that emerges here. When we regressed to a straight line, we only had the first 2 by 2 matrix up here, right? And some xi, and some xi squared, and we had A0, A1, and some yi, some xi, yi. When we went to a quadratic, we added 1 row and 1 column, because now we have 3 unknowns, A0, A1, and A2, so we need a 3 by 3 matrix, right? And turns out the minimization resulted in a 3 by 3 matrix, and we added 1 more row over here. And the pattern continues, okay? If you take these standard polynomial forms, if you add 1 more order, you know, x cubed or x to the 4 and so on, turns out you can generalize this to an arbitrary polynomial of this form A0, A1x, A2, AM to the x to the power m, as long as the coefficients are non-zero. So there was a trick question in your exam when I told you to interpolate A0 plus, when I told you to interpolate A plus bx cubed, right? So although that was a cubic, but it only had 2 unknowns, A and B, right? So we're going to cover this case in a minute. But when you have a full polynomial form like this, A0, A1, all the way to AM, where all the coefficients are non-zero, this is the matrix that you get, okay? Now, I'm showing you this matrix just to show you that there's a pattern that emerges, to show you that that matrix is annoying, so much annoying to try to even program it. We're going to develop a method that is much cleaner and much simpler to try to program this equation, okay? But to show you kind of that there's a pattern, we can do this for an arbitrary model, arbitrary polynomial with non-zero coefficients, okay? I'm not going to ask you kind of to develop this equation, this matrix. We're going to use another way to retrieve this matrix, okay? But like this, you're not going to worry about it, okay? But this is the matrix that minimizes the coefficient, minimizes the error between this model and any data that is observed, okay? In Python, typically we do this in Python, and that's going to tell us the power of Python and its limitation as well. Remember that polyfit and polyval, we've used that. When we regress to a straight line, we set degree equal 1. If you want to regress to a quadratic, you set degree equal 2. If you want to regress to a cubic, you set degree equal 3, and so on. But it will give you a regression to a full polynomial, A0 plus A1x plus A2x squared plus A3x cubed, okay? No other form, all right? But what if you want to regress to this model, A plus bx cubed? Python polyfit is not going to be able to do that for you, because the amount of variability in these models is infinite. You can come up with arbitrary, looking polynomials, okay, knock out any coefficients, and Python is not going to figure that out. At least I don't know of any kind of simple capability in Python that does that. So in this case, we need to do this ourselves. So go ahead and do it yourselves now. Okay, so take this polynomial. It has two unknowns, right? A and B. So you should expect to get a system of equations, two equations and two unknowns, okay, for A and B. And they should be linear because we just showed kind of the coefficients show up linearly. So we're going to get a linear system of equations. So go ahead. Remember, this was the total error. And you're going to minimize this total error with respect to A and B, okay? Working groups. And I would like, yes, most of you have your name tags. Please put your name tags. I'm getting to know most of you, but sometimes kind of, you know, by the end of the semester, I'd be lucky if I memorize like names of like 40 people, but it's easier for you to remember my name. Hey, Lucia. Right. Do you want to work with them behind you, or you just want to work by yourself? Bigger, right? Yeah, they don't show up anymore. It hurts me. Okay. Yeah, you're welcome to work with them if you want, but it's okay if you want to work by yourself too. That's okay. Pre-COVID, I used to have 70 students in this class. We all saw a drop in enrollment in chemical engineering in all departments. So during these activities, the class used to be buzzing. I had to step out because it was so noisy during these activities. And so 70 students, you know, even if half are talking. Yeah, so write the total error, then plug in the model f of x and minimize with respect to A and B. So you need to master this, okay? You need to be able to master this procedure. Yeah, you cannot deduce this system from the global matrix. That's a common, derive it by hand. I mean, you can after kind of seeing it a few times, but it can get very tricky. I do not recommend you do that at all. Hayden, you got it? It's still working. Yeah. How can I help? Okay. You need to keep the summations, okay, and differentiate. So if you plug in f instead of fi down there, it'd be a plus bxi cubed. Keep it as is, so you'll have sum yi minus a minus bxi cubed all squared. Differentiate with respect to a, differentiate with respect to b, set to 0. Okay. You need to master this activity. Okay. We've done it in the previous slides a few times. You need to master this. Okay. All right. Mm-hmm. No, yeah, where you're differentiating with respect to A and B, not X or Y, right? And you need to have your XI's. Okay, so that's right. Yeah, so don't forget your XI. It needs to be inside the summation. So XI and YI will be treated as constants, okay? Okay, so I'm gonna go ahead because we did this previously, and if you guys haven't mastered that yet, you need to go and master it. Okay, we're not gonna spend time on this today. We did this a few times before, so you gotta master this. All right. So summation S is sum yi minus fi squared. Fi is your model, your regression model. You plug that. You plug the model instead of fi, so you get a minus b xi cubed all squared. Then you differentiate with respect to a, differentiate with respect to b, and set equal to 0. And this is what you get. And then you just simply untangle that to build a system of linear equations. When you untangle it, this is what you get. Some of you might be inclined to take the general matrix and kind of deduce the submatrix from it. Don't do that. It's fraught with danger, okay? Because this matrix is not equal to the other matrix by setting the second and third coefficients to 0. That's not the case, okay? So don't do that. Instead, derive it from scratch. The slides are here for you. Please rework these examples, okay? You need to know how to do this. Although in the end, we're going to use another method to get this matrix. But for small systems like this, you need to know this because it's exercising your ability to just simply differentiate, okay? Okay, so that's great. So this model A plus BX cubed, okay, we know how, at least we think we know how to do it. Okay, what if you had data that looks like this and you said, well, this data is oscillatory in nature. So a better model for this would be something that has sines and cosines. I want to do regression with sines and cosines. I'm going to propose that, yeah, maybe a model for this would be of the form A cosine t plus B sine t. Okay, so now the question, I mean, sines and cosines, they're very nonlinear functions. Okay, so now the question, could you do this with regression? And that's what you're going to try to do now. Okay, so do the same thing. Take that summation. Instead of fi, plug in A cosine t and plus B sine t, and differentiate with respect to A and B and set equal to 0. Oops. If you need help, I'm walking around. Just raise your hand. Okay. So TI and TI, right? Yeah, don't forget that. So you're differentiating with respect to A, right? So this doesn't have A in it, right? Well, actually, no, there's a square here. So my bad. I apologize. That's right. Yeah, yeah. So you do have a yi here. You're right. Yes, yes. N times u prime times u n minus 1, right? But you're missing. So you put the 2 and you're going to put this whole thing, but you're missing. You need to multiply by the derivative of the thing multiplying A, right? So it should be a cosine t, right? So it's n times the derivative of all of this with respect to A times u, right? Nu prime un minus 1, right?
So
Yeah, so keep this cosine ti, right? And must be sine ti, okay? But then, yeah, times cosine ti, exactly, right? And when you have just a single argument for sine or cosine, you don't have to put parentheses. It's just easier. Little trick for you, little tip. Let me see. Are you stuck? Okay. Is this the derivative with respect to a? No. Okay. Okay, guys, I'm gonna do this with you once. Did it last time, I'm gonna do it again. Okay. All right. So our model was f of t was a cosine t plus b sine t. Okay. The unknowns are a and b. Our total error was s, sum of yi minus fi squared, and fi is f applied at ti or xi. So if you substitute f in here, you get some yi minus a cosine ti minus b sine ti all squared. Function, two unknowns, a and b. We differentiate with respect to a. S is minimum if ds by dA is equal to 0 and ds by dB is equal to 0. Okay, if you're not seeing, I'll lift the board a little bit up when I'm done with it. So ds by dA, you have a function squared. Okay, so you have a function squared. The derivative of this function with respect to the unknown, in this case, the only unknown is 2 times u prime times u. Okay, so what do you get? ds by dA is equal to 2 times, what is u prime? Is the derivative of u with respect to a. That's minus cosine ti, right? So you get a minus sine cosine ti, but don't forget the summation. Sum of cosine ti, really, okay, times u, which is yi minus a cosine ti minus b sine ti. Yes. Sum. No, we're taking the derivative with respect to a, not with respect to t, right? Okay. ds by dB is equal to, second. Sorry. ds by dB, same thing, minus 2 sum sine, in this case, u prime is the derivative with respect to b. You're differentiating with respect to b. So it's minus sine ti. Sine ti into yi minus a cosine ti minus b sine ti. Okay. So I'm going to lift this board a little bit, you guys to see it. Those are kind of spelled out here on the slide. And they are two equations with two unknowns, and the unknowns show up linearly. So they're not under sine or cosine or kind of logarithm or crazy functions like that. And then you simply put that into a system of equations, and you get, lo and behold, you get your system of equations that you need to solve to do regression to this model. Okay. Now, I like the fact that you're annoyed by doing these derivatives all the time. You should know how to do them, please. But I like the fact that you're annoyed because it's going to drive the point I want to make today. Now, suppose you want to do another model, a cosine t plus b sine t plus c e to the minus t squared. Right? You can do that. If you run through this mechanism, this is the system of equations that you get. You might be thinking of patterns and etc. Yeah, you know, it's kind of be a little bit annoying to detect the pattern. There is a pattern, and so there's a formula for the pattern. But you know, the point is, it's really annoying to get to do these things. And what I'd like to say is that the governing system for these equations with these models with arbitrary functions, not just polynomials. I mean, we just showed that we could do a regression model with sines and cosines, and sine and cosine and exponential, right? So we could do it because the coefficients, the unknowns, as long as they show up linearly, we always end up with a system of linear equations. That's why I call it linear regression. I say I'm regressing to a sinusoidal model where the coefficients show up linearly, and therefore you still have linear regression, but you're not regressing to a straight line. So, you know, make sure you're clear when you're using the word linear regression. Okay? If someone tells me I'm doing linear regression, I'm like, what is the model that you're using? Oh, I'm using, you know, sinusoidal. Okay, great. So now I understand what you're doing. Okay? We'll talk more about linear and nonlinear. Now, this is annoying, these derivatives, because there's an infinite variation of models you can come up with. You might be working in, you know, biochemistry or biophysics. You might have some dealing with bacteria, and, you know, bacteria, they behave in a certain way, and you might know the model fits for those behaviors that are non-standard, not necessarily polynomials. And you might want to regress your data to a model that is non-standard. Okay, so you could do this entire procedure of derivatives, etc., but there's still an easier way to do it. And I'm going to show you that way today. But first, I want to introduce the idea of basis functions. You've probably heard of this word, basis functions. I kind of like to do it by inspection. Consider this model, for example, a cosine t plus b sine t plus c e to the minus t squared. The coefficients of the model, the a, b, and c, we call those parameters in the context of regression, or the coefficients, okay? And what they multiply, the functions that they're multiplying, these highly nonlinear functions, we call them basis functions. In other words, the same way you define a vector using ijk, and you call the ijk your basis vectors, you can describe everything in terms of basis vectors. This is the same thing you're doing here. You're expressing your model in terms of the basis functions cosine t, sine t, and e to the minus t squared. You're hoping that all of your data can be explained by those three basis functions. So in principle, you can have as many basis functions as you want. You can define whatever basis functions you want. It's up to you. You know best your data, the data that you're dealing with. A general linear regression model consists of a linear combination of basis functions and parameters. So, and we will cover in more detail the idea of linear and nonlinear regression, but very simply, when you see the coefficients showing up linearly, okay, so if you hide cosine t, sine t, and e to the minus t squared, the coefficients just show up linearly, right? They're just a times something, and b times something, and c times something. They're showing up linearly, okay? So that is going to lead you immediately to linear regression. We will see a model later. If you had the a inside the cosine, if you had cosine at, that becomes a nonlinear regression, okay? Now we're focused on linear regression and the idea of basis functions. So now, what are the basis functions for these models? I'm giving you a bunch of models on the left-hand side, okay? All I claim are linear regression. Take a moment and write down the basis functions. What are the basis functions for a plus bx, a naught plus a1x plus a2x squared, and so on? You just write them down. Remember that the function 1 is also a basis function. The number 1 is a basis function. It's 1 everywhere, right? So f of x equal 1 is a basis function in and of itself. Yeah. You know the stuff? Remember what? Okay. So maybe I'll give you the log property. Remember that, but I gave you the answer there. We'll hint for the logarithm. Okay. First model, a plus bx. What are the basis functions, Elisha? 1 and x, correct. All right. A naught plus a1x plus a2x squared, Rich. Correct. Okay. A naught plus a1x plus a2e to the minus x squared, Niall. Correct. Yes, so it's 1x e to the minus x squared. Log ax to the b. Who wants to take this one? I already kind of gave that up. Oh, crap. Okay, so you write log ax to the b. Remember, the log turns a multiplication into an addition of logs. So this becomes log a plus log x to the power b. But log x to the power b is b log x, so you get log a plus b log x. But log a is just a constant, okay? So you call it a plus b log x. So your basis functions are a times 1 plus b times log x. Your base functions are 1 and log x, okay? Last one, we kind of did that before. A cosine t plus b log t. Your basis functions are cosine t and log t. It's kind of obvious, right? Okay. So for now, for this exhibition, the way I'm going to derive this simplified way of building these complex regression models, I'm just going to take a simple model with two basis functions, phi of x and psi of x, okay, using Greek symbols, and a and b for your parameters. Very simple, okay? Just to illustrate the point that the proof of this is at the end of these slides, and it's very complicated, okay? But you're welcome to look at it. You're not responsible for it, but I can derive the whole thing just by inspection, okay? And that's what I'm going to do. So these are the basis functions. For this case, if you do the minimization problem, this is what you get for the system of equations that minimizes the error between xi and yi, okay? Now remember, phi I and psi are your basis functions applied at point xi. So phi I is phi of xi and psi is psi of xi, okay? So you get this matrix, some phi I, some phi psi, some phi psi, and some psi psi, etc. Okay? All right, so I want to rewrite this in the following manner. First, the right-hand side, you note that it is the product of a 2 by n matrix times an n by 1 vector. Okay, we kind of did something like this early on. So now I'm revisiting this idea. I did not say anything, Siri. You can go to sleep. Okay. Okay. I don't know what's wrong with Siri sometimes. So notice this. This matrix is going to be very, very special. Okay. So this right-hand side, and if you cannot see it, just take the dot product of phi1, the first row by the y column. So you get phi1 y1 plus phi2 y2 plus phi3 y3 and so on. And the second entry up there is psi1 y1 plus psi2 y2 plus phi3 y3. All right. So this is it. And we're going to call this the vector containing the observed values of the dependent variable. And next, we're going to rewrite this square matrix as the product of these kind of weird matrices, 2 by n times n by 2. Okay. And you can prove it to yourself. The first entry up there, sum phi I, is phi1 times phi1 plus phi2 times phi2 plus phi3 times phi3 plus phi times phi right? So it's the first row times the first column. The second entry up there is the first row of the first matrix times the second column of the second matrix. So that's phi I psi. And same thing for the lower left entry, phi I times psi. So you get this guy times that guy. Okay, second row times first column. And the last entry is the second row times the second column. So I hope you agree that this is the case. Now, this matrix is very, very special. Okay, because this matrix contains, in the first column, it contains the first basis function phi, right? There's only phi in the first column. And in the second column, it contains the second basis function psi, right? What about the rows? What is the first row? It contains the first observation, phi at x1 and psi at x1. And the second row contains the second observation, phi at x2 and psi at x2, and so on and so forth. Okay? Remember this. That's what you're going to remember from all of this, is that this matrix contains in its columns the first basis function, the second basis function, and its rows, those basis functions applied at the first observation, second observation, etc. Okay. So we go back to this system, which is the true system, the system exactly that we were trying to solve. If I call this matrix A and this vector Y, then this matrix is nothing but the transpose of A. Okay. AT, A, ATY. And if you call this vector of unknowns AB, you call it alpha, put it in red because it's the unknowns, then all you need to know for a regression model, all you need to know is the matrix A. In other words, all you need to know are the basis functions. Kia got it. Isn't that awesome? Just the basis functions. The way we wrote them in that previous slide, 1x e to the minus x squared. That's all you need to know. To populate this matrix is a piece of cake, because in the first row or in the first column, I got the first basis function applied at all the observations. In the second column, I got the second basis function applied at all the observations. We're going to see, and so on and so forth. All you need to know is the matrix A. In other words, all you need to know are the basis functions, and that's it. And you can do general linear regression. These are called the normal equations. In this form, ATA alpha equal ATY, they are known as the normal equations, okay? Now, obviously, this methodology applies, and we can prove it, to models with arbitrary basis functions, as long as your parameters show up linearly, okay? As long as the parameters show up linearly. So I'm going to take this arbitrary regression model consisting of m basis functions, m, and m parameters. So alpha 1 phi 1 plus alpha 2 phi 2 of x plus dot 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 plus alpha m phi m of x. The fees can be anything, sines, cosines, exponentials, logarithms, whatever you want, square roots, whatever you want. You can combine them in any way that makes you happy. Probably you want to combine them in a way that fits the data, but you can play around with whatever basis functions you want. So now how do you build that matrix A for this general model? This is it, but you don't even have to memorize it because the columns correspond to the basis functions. So the first column contains the first basis function phi1. The second column contains the second basis function phi2. And the mth column contains the mth basis function phi m. So how I would write this, I would first open a bracket, close a bracket. I would write phi1, and then next to it phi2, phi m. Could be cosine, sine, exponential, x squared. Okay? And then in each row, you put in the observation at which you're dealing, which you're applying to. In the first row, it's the first observation. So go ahead and open parentheses, put x1, close parentheses, open parentheses, put x1, and so on and so on. Second row is the second observation, and the mth row is the nth observation. Remember, it's not the mth observation because this is regression. There's more points than there are parameters in general, okay? You're not doing interpolation. And that's how I would build the matrix, okay? We'll do a few examples, but this is how you would use this. Given n data pairs, x1, y1, x2, y2, etc., xn, yn, in a linear regression model of this form, a linear combination of phi1, phi2, or arbitrary basis functions, you first build the regression matrix. The columns correspond to which basis function you're at. First column, first basis function, second column, second basis function. And the rows correspond to which observation this basis function is applied to. First row is first observation, second row is second observation, okay? You build the y vector, which contains the observed values, y1, y2, etc. And then you solve the system ATA alpha equal ATY. So really all you need to know is A, and you're done, okay? All right, so let's put this to practice. No derivatives now. So this should be easier. You should be able to do matrix multiplication. So we're gonna take our standard straight line regression, A plus BX. And we know the regression system, the answer is this system. But I want you to obtain this system by building A and B and alpha and doing ATA times alpha equal ATY, okay? This is A. So first step, you gotta do this A matrix, okay? You gotta build this A matrix. Assume you have n data points, okay? So first, you write the basis functions. Let me do it with you, this one. The next one, you'll do it by yourselves, okay? So Y model is A plus BX. First thing I need to know are the basis functions. They are 1 and x, okay? So my A matrix from the normal equations, in the first row, it contains the first basis function. It's always 1. And in the second row, it contains the second basis function. It's x. Now, the first row is the first observation, which is x1. Second row, second observation, x2, and so on all the way to xn. Alpha is AB, the vector of unknowns, and y is y1 to yn. Next, you build ATA. So that's, you take the transpose of A and multiply it by A. So that gives you the coefficient matrix. And if you do this multiplication, you get indeed n, some xi, and some xi squared. Like, it took us like an hour to derive this in the beginning. Now it takes a moment. Again, this matrix, dot product of first row by first column gives you n. So 1 times 1 plus 1 times 1 plus 1 times 1 n times. Same thing for this guy, and that guy, okay? And for the right-hand side, you get ATA. So in the first entry, you get some yi, and the second one, some xiyi. And that's how you do it. Okay, so now do it for a quadratic. remember, so I'm gonna give me a moment so I can merge these slides. I'm gonna copy this one over here. Okay. There you go. So this is the matrix A. First, write your basis functions, build the matrix A, and then the rest is kind of simple. That's your Ryan. And you can work in groups. Yep, ATA alpha equal ATY, right? Because you're multiplying everything by A transpose. Is this ATA? Oh, no, you're building it. Yeah, yeah. Good. Yep, good, good. Yeah, so do it for, yeah, don't forget the 3 dots. That's okay. That's okay. Much easier, right? Everyone is like cruising through this. Jake? Okay. Yep. So it's kind of do it for n, right? Yeah, and then do a, try to do the product A transpose times A. Okay, so that you can recover that form. Okay. So that's what you need to show. Hannah, you got it? All right. It's okay. It's not an obligatory activity, right? So don't forget to include kind of the 3 dots, right? So that you know that these are endpoints so that you end up with a summation in the end, okay? Okay, so you got AT, you got A, okay? So the transpose just kind of, yep. So you got ones and then x1, xn, and then x1 squared, right? So you take this one, turn it like this one, turn it like this, and this column and turn it like this, okay? Okay. Okay, so the transpose is off, right? So A transpose is the transpose of A. So the rows becomes the columns become rows. No, it's ATA. So if this is A, AT needs to come before it, right? Otherwise, the sizing will not work, right? The matrix sizes will not work. Okay. All right. Most of you got it. Okay. Okay. Yes, do the product. Do the product. Yeah. Just to kind of see that you get this n and some xi, etc. Give you another 30 seconds. No, ATA. So remember the matrix, the system is AT. The system is ATA, okay, not AAT. So, oops, sorry. There you go. Up, up. ATA times alpha equal ATY. The transpose of A, you take the first column, make it the first row of A, second column becomes the second row. Perfect. Go work. will work. Okay. Kevin? Okay, let me see. You think you got it? Okay, so you got stuck somewhere. Okay, so let's see. Do you mind? Oh, okay, okay. Yeah, so you know, so I think your transpose, your numbers are wrong. Your matrices are in the wrong order. You have AAT. It needs to be ATA. It needs to be A transpose times A. Nathan, you're like in your head. You got it. Pardon me? Yeah, so ATA times alpha equal ATY. Those are called the normal equations. Yeah. I don't know what they call it. I tried to to find out today. I just call it the A matrix from the normal equation. So yeah. I know. I mean, me neither. For the life of me, I don't know what they call it. We call it the A matrix from the normal equations. Okay. All right. So most of you got it. Okay. Excellent. Should be much easier than the previous strategy. Okay. See, a couple more. All right. Good. You got it. Okay. Much easier, right? Okay. Great. So it's kind of the answer, right? You have your basis functions, 1x and x squared. In the first column, you put the first basis function, second column, second basis function, third column, third basis function, and then the observations go in the rows. And then it's a matter of matrix multiplication to get the normal equations. And lo and behold, you get that complex matrix that we spent so much time to do with minimization. Okay, so now do this for this model, a log x plus b cosine x. Build A first. So find the basis functions, build A, A transpose A times the coefficients alpha equal A transpose times Y. Well, you asked for more activities in class, so. Ryan, all good? Yeah. Okay, perfect. Yeah, once you get that transpose thing, it becomes piece of cake. Don't forget the 3 dots. So put like the first, second observation, and then 3 dots, and then the nth observation, okay? Your resulting system of equations as a sanity check needs to be of the same size of how many unknowns you got, right? So you got 2 unknowns, A and B, you need to have 2 equations. Okay, so it's a 2 by 2 coefficient matrix for the system of equations in the end. Okay. Remind me of your name. Isabel. Isabel. No, that's, I remembered you had the name tag last time. I'm like trying to remember the name. Okay, so all good. Looks like you got it. Yeah. Okay. Yep. The transpose is a little bit kind of can be confusing. Yep. So take the first column and make it a row. Take the second column and make it the second row. Hayden, good, perfect. Yep, now just multiply them. ATA in that order. You can't change the order, otherwise the matrices are not going to multiply. Mm-hmm. No, no, you got it. Yeah, I'm just always was wondering about. I thought I saw something else. That's good. Yep, yep. Mm-hmm. Yep. Okay. Okay. Cosine squared doesn't matter. I like to write them separate, cosine, etc. But it doesn't matter. Yeah, just easier to visualize. Yeah. Okay. Perfect. Yep. Yep. And notice that it is symmetric, right? So, these entries on this diagonal, they're the same. Okay. So really what this matrix represents is all possible combinations of the of products of basis functions. So you have two basis functions, log x, and cosine x. So all combinations of products, you have log x, log x, cosine x, log x, and cosine x, right? And that's what you see here. Log x, cosine x, log x, cosine x, cosine x. All possible products. Okay, that's the pattern in these resulting matrices. Okay, I'll show you the answer. Okay, this is the answer. All of you got it, really. Okay. Okay, so now for the most exciting part is how do you do this in Python? Remember how annoying it was to build those matrices? I mean, even imagine trying to build that system of equations for a fifth order polynomial, trying to do all of those summations, very annoying. There's a very neat and clean way of putting in the normal equations in Python, okay, in one line of code, literally one line of code. So again, this is our infamous A matrix. Nathan was asking me in the back, like, what do you call this matrix? If they're called the normal equations, would you call this the normal matrix? I really don't know. For the life of me, I haven't found a clear name for what A is called. So when I ask a question, I tell you, use A from the normal equations. Use the A matrix from the normal equations, okay? If you find a name, do tell me, okay? All right, so this matrix consists of vectors. So if you look at the first column, it is the vector of the first basis function applied at all the observations, right? Phi1, x1, Phi1, x2, and so on. So this in and of itself is one array, right? Same thing for here. This is the array of the second basis function applied at all the observations, x1, x2, xn, okay? In Python, you can build this entire matrix using a feature called column stack, okay? The whole matrix can be built with this one line of code. So let me explain to you what this is. You call this column stack function from NumPy. Now, in practice, you are given xi as a 1D array, correct? x1, x2, x3, there are an array. And Phi1 is cosine, for example, Phi2 is log. So if you put Phi1 at xi, so cosine of xi is going to produce a cosine at x1, is going to produce an array, cosine x1, cosine x2, cosine x3, and so on, right? So that gives you, so Phi1 of xi gives you this first column. Phi2 of xi gives you the second column, and so on. To combine them all into one big matrix, you use column stack. And that's all you need. That's it. Once you know A, you can take its transpose, multiply it by A, and you get the system of equations. And you multiply it by Y to get the right-hand side, okay? Very simply, given xi and yi data arrays, you create A as a column stack of Phi1 xi, comma Phi2 xi, and so on. And then you build the left-hand side, ATA. I call it a variable, ATA, which is the left-hand side. It's A transpose dot times A. So this at is a matrix product. Same thing for the right-hand side, A transpose at yi. So it's the product of the A transpose with the column vector yi, and then you solve, and you get the coefficients. That's it. 1, 2, 3, 4 lines of code for the whole thing. Any regression model. Pardon me? Okay, you know, import NumPy. So one more line of code. Here's an example for some of these models. For the straight line, I probably also need the one more line to get the, but those are like insignificant lines, right? So in this case, my basis functions are 1 and xi. So that's what I put in my column stack, np.1s of size n and xi. And that's it. For a and bx and x, for 1x and x squared, so a quadratic, in my first column of basis functions, it needs to be an array of ones. So I create an np.1s of size n, and then in the second column xi, in the third column xi squared. Could be cosine x, log x, whatever. Doesn't matter. Pardon me? Well, okay. All right. So let's play around with this a little bit. Okay, with this university GPA. Okay. So apparently these data, they try to predict your university GPA based on something else. I don't know. Okay, let's see what this is. the femur. Well, there's this website that finds you can like build correlations between anything. You know, you can just randomly like, you know, pick how much butter you ate in your life versus kind of, you know, what your salary is going to be. It's not causation, but you can build kind of these crazy correlation graphs. It's a lot of fun. All right, so let's see. Where's my Jupyter notebook? Okay. So open up the GPA notebook with gaps. Activities, let me see. Okay. I'm gonna switch over here. So although we are gonna be doing, in this example, we're gonna be doing regression, just sticking with polynomials. Okay. The same strategy applies for arbitrary basis functions. Okay, guys. All right. Let's zoom in a little bit. Okay. So, okay. We start by importing kind of the boilerplate. Now, I have a function over here called r squared. That's kind of, so I know last time we did an r squared calculation, we kind of defined the function in line to compute the r squared value. This is a more general form. And by the way, you are welcome to use like functions I define in class for you. Okay, so that is very fair use because I'm distributing those functions as, you know, modules to be reused. Okay, so use those. That's not copying or illegal or whatever. Okay, so define r squared value. It takes the xi data, the independent variable of the observed data, the yi dependent variable, and a y model. So we will talk about this in a minute, but that's really what your regression model is. A plus bx, for example, or a cosine t plus b sine t, as long as it's just a function of x only. So I need to be able to call y model at x. see here, I need to be able to call this. So if you define, so Y model is just simply the name of a function that you define later when you create your regression model. You pass it to this R squared and it computes the R squared value for you. Okay, you'll see this in action in a minute. All right, so you need to also, for this example to work, you need to also download GPA data.txt and put it next to the directory of your notebook. Okay. All right. So here what I'm doing, I'm just kind of loading data. You'll learn more about this in statistics, in the statistics class with Professor Silcox. You'll do more fancy stuff. Over here, I'm just loading a text data file. Okay, let me define this. And from this, I am taking 2 data points, high school GPA and university GPA. So that's it. This is high school GPA a predictor of your university GPA? Okay, we'll ask some questions now and see kind of how good this model is going to be. Okay. All right. So that's what I'm taking X, I, Y, I, and then I'm going to plot the data. So this is what this is saying. On the X-axis, we're plotting high school GPA. On the Y-axis, we're plotting university GPA. It seems that it's divided in 2 regions. For GPAs, for high school GPAs that are less than 3, sorry, I think you need to have at least 2 to go to you. Okay, so for GPAs that are less than 3, it seems to be wildly variant, right? So you could have a 2.5 high school GPA, yet get a 3.25 university GPA. Okay. That was the case for me. When I grew up, I didn't have GPA for school, but there were subjects like math. I did not like math because I didn't understand what they were doing. But once I got to the last year of school and they started digging deeper, I was like, oh, wow, this is great, you know? And then I had only hundreds on my math. I was like, so, you know, this is totally understandable. You could have a low high school GPA, but a high university GPA. So below 3, the data is kind of split. However, above 3, it seems that high school GPA is a strong predictor of university GPA. Okay. I mean, that makes sense. It's kind of like it's rare for you to, you know, if you're good in high school in terms of the GPA, it's unlikely that you're gonna get worse, right? As you learn more, as you progress more. But in this case over here, it might be the case that, like, you know, you didn't like there was not enough information in high school given to you to understand the math or the physics or whatever. Okay. All right. So in this first, I guess this is not with gaps. Do you guys have gaps in your? Okay. Oh, bummer. Okay. Okay. Maybe Kia is like, I'm already done with this. I'm gonna go home now. Okay. So I'm sorry about this. There's just like so many notebooks I have. Okay. So the model here is a straight line, A0 plus A1x. My basis functions are 1 and x. Okay. So all I need to do to create my matrix A, so this A matrix is this guy over here, 1x1, 1x2, and so on, is to do a NumPy column stack, 1s in the first column and xi in the second column. Okay, so let me show you this. If xi is 3.45, 2.78, etc., then let's see what A is. So in the first column of A, you got 1s everywhere, correct? Look at that. And in the second column, you should have the xi values, which are 3.45 indeed, 2.78, right? 2.52, 2.52, 3.67, and so on. Okay, when in doubt, print it out. Okay, great. So we got A. Now we build our system of equations. ATA, that's the left-hand side, and the right-hand side is ATY. You do it. Okay, so now if you print ATA, what should it be? Should be a 2x2 matrix, right? Thanks for the excitement. Okay. And then finally solve the system of equations. You give it a left-hand side and a right-hand side, and boom, you got the coefficients A and B. Much easier than what we did before. I like to use this over polyfit because this gives me the flexibility to play around with my basis functions, okay? Now, I want to plot this. I want to plot this fit. So I first need to grab my coefficients A0 and A1 from the solution. We did this last time. And then I'm going to define my model. This is my model over here. It's called linear fit. Now, remember, in my R-squared definition, one of the arguments was Y model. This is it. It's called linear fit in this case. And I'll show you how we calculate the R-squared here, okay? But now I want to plot this. So my linear fit model takes an X value, arbitrary X value, and then go ahead and just plot this, okay? Goes right through the data. It's a very bad predictor over here, but probably very good over there, okay? So now let's see the R-squared value. R-squared. For R-squared, you need to pass it xi, which is your input, excuse me, input X values, input Y values, and your Y model. What is your Y model? It's simply the name of the function that you defined for your model. In this case, it's simply linear fit. That's all you have to do, linear fit. But there's a condition, there's a constraint on this linear fit. I'm telling you here, Y model is a Python function of X only, of one variable that can be evaluated at xi and represents a model fit of the data, okay? So when I do this and print the R-squared, it gives me a 60%, you know, kind of improvement over using the mean value to describe those data. Okay. Now I hypothesize, and I'm not going to do this here, but I hypothesize that if I were to take a subset of data from GPA 3 and onwards, the fit is going to be probably 80%. Okay, the R-squared value. So you can slice the data and just consider that that subset. Okay. Now, this is probably a bad example to do like a complex model. Here's what I'm going to do, actually. Let me try this. So at the bottom over here, I also have a quadratic fit for you. Oh, yeah, the columns. Yeah, this is what it is. This is. OK, so let's do the quadratic fit together. So here we're going to put in A0 plus A1x plus A2x squared. OK, if you have you all done this now? Or are you just getting to it? I know you did it. Okay, if you haven't done it, go ahead, take your time, try to fill in the blanks, okay? Remember, we already declared n as len, so n is len xi, okay? Okay, what would we put in the, just start with A, first basis function, second basis function, third basis function. First basis function is 1. But it needs to be an array of ones, right? Because there's rows. So the first column is 1, but 1 n times. So it needs to be an array. So that's why I create an np.ones of size n. Okay, so I'll give you this one, np.ones of size n. Over here, Kia, xi. Over here, xi squared. Okay. Now you should know that xi is an array of size n, and xi squared is an array of size n that contains xi squared, x1 squared, x2 squared, etc. Okay, ATA is simply A dot transpose at A, and the right-hand side is A dot transpose at Y. Okay, yi. You solve, you get the coefficients. Then you build your quadratic fit. Okay, almost done. So you get the coefficients from the solution, A0, A1, A2, and then you create a routine that that implements the model for you. So you can evaluate it and make predictions. So let's see what this does. So plt dot plot xi, and then what I'm going to do here is quad fit. Oops. Quad fit at xi. Yeah, not much improvement. R squared is still 60%, obviously. Okay. Next time, this is great because next time we can talk about nonlinear models, and I'll show you a little trick how to manufacture data to test things. Okay. How to just create a, let's say a sinusoidal function and then add noise to it and then try to fit it. Okay. Thank you, everyone. I will see you on Thursday.
Could you scroll up just slightly, Dr. Saad?
Yes. Is
Oh,
this
okay. I
enough?
missed the XI on the quad fit. Okay, thank you.
Of course.